So now we're going to look at charging a capacitor through a resistor. Before we just looked at discharging a capacitor, so the charge was running off the capacitor through the resistor and sort of neutralizing itself. Now we're going to look at what happens when you hook up a battery to a resistor and a capacitor, and this is really how capacitors are charged. So if we were really going to make a circuit that you might see like in a camera, you would have that one's not very dark. You would have a circuit that looks like this, and then you'd have another resistor over here. And this is what I was talking about before, where you can charge a capacitor or you can let it discharge. And this could be like a light bulb, this resistor. Right? This could be a flash on an SLR, on a fancy camera of some kind or something like that. Right? And the idea is this thing needs a very large current, so a lot of charge really fast. Capacitors are great for that because they're just conductors and they let it run off. A battery requires chemical processes, and so they're typically slow. And so when a camera is operating a flash, not like on a cell phone where it's just a little light bulb, but a serious flash, what it does is it charges the capacitor through a resistor and then discharges the capacitor just freely. And so it charges it on this circuit, and then it moves the switch over and discharges it through that way whenever you press the camera button. And so we looked at this side on the last video, and so now we're going to look at this side. What happens when you throw this switch and charge this guy through that resistor? And as you might imagine, it'll charge. How long it takes this capacitor to charge depends on how big this resistor is and how big the capacitor. If it's a really big capacitor and a really big resistor, it takes a long time, because you can put a lot of charge on the capacitor, and a big resistor makes it come through really slow. And so these two factors, the resistor and the capacitance, determine how long it takes the thing to charge, just like they both determine how long it takes to discharge, right? So we're just going to look at this half of the circuit, the left half here, and so I'm going to erase all these guys. And I'm going to say, when I throw this switch, the charge begins to run onto the capacitor, right? And so I get a VC, which is the voltage on the capacitor. If I were to do like a Kirchhoff's rules around this thing, and I say the current's running this way, notice now when the current is positive, the capacitor is charging, and so I equals dq dt, where Q is the charge on the capacitor, right? We have Q equals C times VC, which is the voltage across the capacitor, which is different as it's charging from the voltage on the battery. When you first throw the switch, what's the voltage across the capacitor? So you should be able to answer in your head that it's 0 because there's no charge on it at the instant the switch is thrown. It's like, what's the velocity of a ball the instant I release it? Right? Well, if I just let it go, the instant its initial velocity is 0. The initial voltage across this is 0 because there's no charge. And then charge starts to run on. And so if I was to write Kirchhoff's rule for this loop, say starting here, I would have a V for going up the battery, minus IR for the resistor, and then I would have minus VC for the voltage across the capacitor. Notice I'm going minus because I'm going from the plus side to the minus side, equals 0. And so before I just had a differential equation in these two guys, but now I've got a little more complex one because I've got a voltage from the battery here. This is just a constant, right? But the current is changing because as this thing starts to fill up, it wants less and less charge, right? And so as is the voltage across here. We already said that VC is just Q over C, and this is dq dt, so I can write this as V minus dq dt times R minus Q over C equals 0. And so this is the differential equation I need to solve for Q to figure out the charge on the capacitor as a function of time. And so it's a little more complicated than the last one, but we still want to separate variables. Notice our constants are the voltage, the resistance, and the capacitance. The voltage on the battery, right? This is the voltage on the capacitor, and that's varying. And so what I want to do is, again, to the extent that it's possible, I want to separate variables. And so I'm going to move the dq dt to the other side, and I'm going to say dq dt times r is equal to v minus q over c. Right, I just pick this term up and move it to the other side. And then I can say, I'm gonna, let's see, what am I gonna do? I'm gonna divide both sides by this and multiply them by, so let me just do it that way. I'll just divide both sides by v minus q over c. Right? I'm going to try to get all the q's on one side and all the t's on the other side, and so I get dq over dt times r divided by v, sorry, that doesn't equal, it just gives me this, minus q over c is equal to 1, because I took this both sides of this equation and divided them both by this, and so that gives me this. It's a little silly right now. Right, but now I can multiply. So let me just simplify this thing a little bit. Right, this is dq dt times r over v minus q over c. It's equal to 1, and so I'm going to multiply by dt over r. I get dq over v minus q over c. Sorry, it's taking me just a minute to simplify this. It's equal to dt over r. This should start looking like what we had last time. I'm going to multiply both sides in the denominator by c, and you'll see why in a second. So dq over vc minus q. In other words, I multiply this guy by the capacitance and this guy by the capacitance. I'm free to do that. In a sense, I'm multiplying both sides of the equation by 1 over c, if you prefer, equals dt over c times r. This is pretty similar to what we had last time. Notice I have separated variables. The t variables on this side, the q variables on this side. I have an extra term or two, but they're just constants. And so now I have achieved separation of variables. And now I'm going to simplify this. I'm going to say, look, u is equal to vc minus q, and that means du is equal to minus dq. And so this equation becomes minus du over u is equal to dt over rc, right? Because dq is minus du and u is vc minus q. And so now I can integrate both sides. Right, and if I want, I can start at t equals 0 and go to some time t. And then I can go from u naught to, I don't know, u prime. I guess I don't want these variables to, I can use prime variables for my integration limits. And then I can simplify later, switch back later. And so this becomes minus log of u evaluated at u naught and u prime. And this guy is equal to t prime over rc. Right. And so this gives me minus log of, am I still on the screen here? Just barely. Let me scooch up just a little bit. Let me write it over here. Minus log of u prime over u naught equals t prime over rc. And so u naught is just vc, because it's u naught is evaluate u at t equals 0, right? It corresponds to u naught corresponds to 0 time. Well, the charge on the capacitor initially was 0, and so this is just vc, and then u prime is just vc minus q prime, which is the charge at some later time t prime. And so what this becomes is, so I'm going to erase here. All right, let me just pause for a second. Okay. So this is the equation we got to with these values. And so let me just write this up here somewhere. Right? What we got was minus log of u prime over u naught equals t prime over RC, but these are just evaluated at some arbitrary time, and so I'm just going to erase the primes back again and go back to unprimed, and then u naught is VC, so this becomes well, why don't I simplify this first? I'm going to move the minus sign to the other side, and so I'm going to get log of u over u naught is equal to minus t over RC, and then I'm going to take e to the both sides, and I get u over u naught equals e to the minus t over RC. This should be looking familiar, and that gives me u equals u naught e to the minus t over RC, and so u is VC minus Q. That's what my u is. I changed all my primes to unprimed, because once I got past that, I can just substitute back the unprimed for the primes, and then I get equals VC e to the minus t over RC, right? And if I get the q on one side and the other guys on the other side, I get q is equal to VC minus VC e to the minus t over RC, or I get q is equal to VC times 1 minus e to the minus t over RC. So this is the relationship I have between the charge on the capacitor and time for a voltage V on a battery, a resistor R, and a capacitor C in a circuit starting from t equals 0 with no charge on the capacitor. Right. Let me just write all these guys down here. And so let's see if we can do a sanity check on here. When t equals 0, we expect there to be no charge on the capacitor, because that's what we said, right? And so if I stick in 0 here for t, I get e to the 0, which is 1. 1 minus 1 is 0, and I get q equals 0. So I get, at t equals 0, I get q equals 0. And so that just makes me happy. Right? Now, if I let this thing charge forever, if I just close the circuit and I leave it plugged in all the time, what happens? Well, the capacitor, well, you should answer this question on your own, but the capacitor gets fully charged, right? The capacitor charges up until it can't take any more charge. If I wait long enough, enough charge will leak through to fully charge the capacitor. And so at t equals infinity, I expect Q is equal to CV, right? That's my relationship between the charge on the capacitor and the voltage applied across it. And so let's see if I get that here. If t equals infinity, then this piece becomes 0, and I just get Q equals CV. And so this equation matches the endpoints, at least, the 2 points where I expect it to be, where I sort of expect to know the answer. And so what does the graph look like? Well, this part is just a decaying exponential. And so this part looks like this, right? Where it's just, it asymptotically or exponentially goes to 0, right? Something like that. Right, but now I'm taking 1 minus that, and so this piece would start at 1. E to the 0 is 1. So instead, this piece, the piece in parentheses, looks like this, where it's approaching 1 the other way, right? If I take 1 minus this, I get a 0 here, and the other guy becomes a 1. If I multiply it by VC, I just get VC at this point. And so if this is my charge and this is my time, it asymptotically approaches VC. And so this is what the charge on the capacitor is. I can take the time derivative of this, and I can say, look, if Q equals VC minus VC e to the minus t over RC, right? I expanded it back out, then dq dt, that is the current, which is I, is just the derivative of that. Well, this guy is 0, and this just becomes V minus VC times e to the minus t over RC times minus 1 over RC, right? It's just, this is just e to the x times the derivative of what's in the exponent, and if I take a time derivative of this, I just get minus 1 over RC, and so this becomes V over R e to the minus t over RC, right? The minus signs cancel, the c's cancel, I get V over R. Well, what is this, right? This is the current. At t equals 0, it's just V over R. In other words, when there's no voltage across my capacitor, which is true at t equals 0, then all of the voltage across the resistor, and the current I get is just V divided by R. At t equals infinity, now I have full voltage across here. It's the same as across the battery. The current is 0, and that's what I get at t equals infinity. E to the minus infinity is 0, and so I multiply this, I get 0, I get no current. And so this is what I expect to see in my current through my resistor. That graph looks like this. If my current looks like this and my time looks like this, right? And this point here is V over R. So this is the charge. This is the current through the resistor. If I wanted the voltage here, I would just calculate Q over C, right? And so I could say the voltage on the capacitor VC is just Q over C, which is just V times 1 minus e to the minus t over RC. Right? In other words, at t equals 0, there's no voltage across the capacitor, and at t equals infinity, the voltage across the capacitor is the same as what's across the battery. So I would say these are your three basic equations: the charge on the capacitor, the voltage across the capacitor, and the current through the resistor, or the current going onto the capacitor, either way. Okay. You could, of course, calculate the voltage across the capacitor by multiplying this guy by R, which would be easy enough to do, or just subtracting this guy from this guy. And that will get you the voltage across the resistor as well. All right. So in this problem, a capacitor C of 20 microfarads is being charged through a resistor by a 12-volt battery. And we want to know how long do we have to wait until the capacitor is half charged, right? And so that means that Q is equal to CV over 2, right? When it's fully charged, Q equals CV. When it's half charged, Q equals CV over 2, right? And so we already have this expression, Q equals CV times 1 minus e to the minus t over RC. Right? This tells me at a given time, at some time t, how much charge is on the capacitor. Well, I just said that's CV over 2. Right? The CV's cancel, and I get 1 minus e to the minus t over RC is equal to 1/2, or I can say e to the minus t over RC, if I move that guy to that side and that guy to that side, is equal to 1/2. Right? If I take the log of both sides, I get minus t over RC is equal to the log of 1/2. That means that t over RC, if you remember your log formulas, right, is equal to the log of 2. Because I can move the minus sign over, and that just inverts the argument to the log. And so I get T is equal to RC log 2. Notice I haven't plugged a number in here yet. So this would be true for any circuit. If I want to know when it's halfway charged, it's the resistance times the capacitance times the log of 2, right? And so if I take 20 microfarads times 3,000 ohms, I get 0.0416 seconds. If I wanted to make that take longer, I could just use a bigger resistor or a bigger capacitor or both. So if I wanted to find when it was 10% charged, this would be CV over 2, and instead it would be CV over 10. This would be a tenth. And so this would be 9/10, so this would be 10 over 9, and then I would just reevaluate. Anyway, so whatever factor you want to change it by gets in here, and we'd have to work your algebra out. When you put it, if I put a tenth in here, then I'm moving it to the other side. This becomes 9/10 instead of a half. But it's easy enough to do, and then you just plug your numbers in at the end, but they'll all look very similar to this sort of expression or this one.